Hey team, welcome back. Today we're talking again about solving systems of equations. We've already talked about the first four methods. In today's video we're going to do Jacobi and Gauss-Seidel. Now before we dive in, let's go back over some of these other methods. The first two, these are our bad methods, our poor methods. And these are bad because, well, substitution is manual, right? It takes a long time and it's tedious. And really this is a method for children. This is what we did in middle school. Kramer's rule gives you an explicit solution, but it is computationally expensive. So expensive, in fact, that we're not going to use it. We talked about Gauss-Jordan in a previous video. This is matrix inversion. And this can only be used on linear systems. Next, Newton-Raphson. Newton-Raphson is it's the de facto method for solving systems of nonlinear equations. It's fairly fast, and for example, most software tools for solving systems of equations, they're going to use Newton-Raphson as the default. Now, when I say Newton-Raphson is the de facto for nonlinear systems, why wouldn't we use it for linear systems? Recall that the Newton-Raphson requires that you calculate the Jacobian of the states, and then you invert that Jacobian, and then that process becomes repeated. Well, if you're inverting a Jacobian and it's a linear system, why not just use Gauss-Jordan and do a single matrix inversion and get the answer explicitly to begin with? So Newton-Raphson requires that you do this matrix inversion repeatedly, but it's fairly fast, and it's also reliable for nonlinear systems. So these last two, Jacobi and Gauss-Seidel, both of these can be used for nonlinear systems. So if we have multiple methods for nonlinear systems, and I say that Newton-Raphson is fairly reliable, then why do we need Jacobi and Gauss-Seidel? Well, there's many instances where Jacobi and Gauss-Seidel cannot be used, and we're going to talk about that, the state of the equations, the types of systems that these can be used to solve. And if Jacobi and Gauss-Seidel cannot be solved, well, then you're going to use Newton-Raphson. Why would you want to use Jacobi or Gauss-Seidel? Because these methods do not require matrix inversion. So these methods can actually be very fast. But as I said, you can't always use them. So let's clean this up and let's do an example, and let's talk about how we actually formulate these two approaches. Let's look at this example system. It's a 3x3 linear system. We know that we could arrange it as ax equals b. We know that we can solve it using matrix inversion. What we need to do is we need to take these equations and rewrite them. We're going to take the first equation and we're going to write it in terms of the first variable, take the second equation, write it in terms of the second variable, third equation in terms of the third variable. If you do that, if you take the first equation and you solve for x, clearly you take these terms, you move them to the other side, and you divide by the 7. So we're looking at 10 minus y minus 2z divided by 7. The next equation, we're going to solve for y. 8 minus x minus 3z. And this one we're going to divide by 8. And then the last one, z is equal to 6 minus 2x minus 3y. And this is divided by 9. Okay. So what's the point of doing this? Well, what we're going to do is we're going to start with the Jacobi method. And in the Jacobi method, you pick some initial conditions. We would say that, let's make a vector, I'll call it q. Q is equal to the states x, y, z, and we pick some initial values x naught, y naught, z naught. What we're going to do is we're going to run through these equations. Okay, and we're going to loop through these equations. We're going to take the values of x, y, and z, we're going to put them into these equations, and then we're going to solve for an update. When I say let's solve for an update, here's what I mean. let's suppose that we're at the nth iteration. So here is yn, zn, xn, zn, xn, yn. And what we're solving for on the left, xn plus 1, yn plus 1, and zn plus 1. And then this is your looping structure. So you're going to loop over these equations until we hit some convergence criteria. And let's say that, again, let's say that the vector q represents all of our states, x, y, z. We're going to continue looping over these equations until q at n plus 1 minus q is less than some specified threshold epsilon. When these, all three of the states, when they converge underneath this threshold, then you are done. Okay, so this, what we've just done, this is the Jacobi method. All right. So the other method we said was Gauss-Seidel. How does Gauss-Seidel work? It's actually, it's almost identical. The only difference, what we're going to do, right now with the Jacobi method, we're running over all three of these in a batch, which is we're going to update x, update y, update z, and then we're going to loop, and then those updates become the new states, and then we run through the equations again. So effectively what is happening is underneath this last equation is another round of equations, and we're saying, okay, here is xn plus 2, and this one is equal to 10 minus yn plus 1 minus 2 z n plus 1 divided by 7, okay? Dot, dot, dot. So you can imagine these equations just running continuously. What we're going to do in Gauss-Seidel is we're going to eliminate this barrier between the equations. Okay, so we're not going to run them as a batch anymore, as a batch of three equations. Instead, let's now think of it really continuous. And this time when we do it, let's always use the most recent state. So instead of using yn, zn, xn, zn, xn, yn, and then running the updates, instead, as soon as we have calculated xn plus 1, we're going to use xn plus 1. So here, there. Now we're using xn plus 1. Then we calculate yn plus 1. So this becomes n plus 1, n plus 1. And then in the next equation, we have yn plus 1 and zn plus 1, and then we're calculating xn plus 2. So in this method, this is Gauss-Seidel. In the Gauss-Seidel method, you don't run them as kind of this artificial batch. You always use the most recent updates. Okay, and that's literally it for the Jacobi and Gauss-Seidel methods. They're not particularly complicated, but they are fast, and they don't require matrix inversion. So what's the hook, right? There has to be a hook. Why don't we just do this all the time? Here's the hook. If you look at the equations that we're working with, there is a very distinct characteristic about them. Look at the magnitude of the diagonal terms and realize that these diagonal terms, they have the largest coefficients in their respective equations. If this leading coefficient was a 1 and there was a 7 on the y, these two methods, Jacobi and Gauss-Seidel, they would not work. Sometimes you might have to rearrange the equations. For example, if I had presented this with the first two equations swapped, and you solve them for x, y, z, these methods would not work. However, if you simply swap the equations and then solve them for x, y, z, it works. So sometimes you have to just rearrange the equations to get into a convenient format. Okay. These can also, the Jacobi and Gauss-Seidels, they can also be used for nonlinear systems, but just be aware that these two methods are fickle. They don't always work, and they're not always going to converge. So if you have a situation where you know that your system is behaving appropriately and you can arrange it in this diagonal form, you can get some very nice speeds out of these two methods. If you can't, or if it's highly nonlinear and these methods are not converging, then you switch to a Newton-Raphson approach. Okay, let's present the pseudocode for this. Remember the condition about Jacobi and Gauss-Seidel methods. Number one, you need to ensure that the diagonal coefficients have the highest magnitudes in their respective equations. So the largest magnitudes. Now that may require that you rearrange the equations before. Number two, take those equations and solve for, let's say solve for the diagonal unknowns. So equation number one, you solve for x1. Equation two, you solve for x2. 3, we're going to iterate over the equations. And we're going to solve for the update. So the updated states. Now remember, when you do this, if you run it as a batch, you're doing Jacobi. If you're always using the most recent values, you're doing Gauss-Seidel. Number 4, we're going to repeat until a convergence. So we can say that, let's call the vector x in this case. So x n plus 1 minus x n. When this converges, when this it's now less than some threshold, then you can stop. Or remember, with these numerical methods, there's no guarantee that it does actually converge. So we always want to specify some maximum number of iterations. So if your current iteration is greater than, if it exceeds some maximum iteration, then call it and print. Okay, that's it for the Jacobi and Gauss-Seidel. This is the last of the solutions for solving systems of equations. Okay, so you should have all of the tools now for solving your last lab. So best of luck, and I will see you next time.